So C is negative A over 2. So C is plus an 8. Okay? So, okay, right over here, it's all the way down, but hopefully I can let this X sub P is equal to 1. I've got big A T squared, and big A was minus a quarter T squared, nothing times T, and plus an 8. Okay, so the particular solution comes out to be an 1/8 minus a quarter T squared. Okay? And in this case, we're going to actually have to write it out because I have to solve for y also. Okay, so that can come over here. So the solution for x, okay, is a complementary solution, which was what up there? C1 cosine 2t plus C sub 2 sine of 2t. Right? C1 cosine 2t. And the particular solution was an 1/8 minus a quarter t squared. Okay, so there's our solution for x. Okay. Now we got to solve for y, right? Okay. And again, how many constants is supposed to be a general solution? It's supposed to be 3. We got 2 so far. Okay, don't be surprised if we pick up 1. Okay. Well, that's the easiest way to solve for y. Okay? You have x. If you plug it over here, you'd have to integrate twice, and you'd have a non-homogeneous equation, right? I think the easiest thing to do is go over here and just solve for dy dt, and then just integrate once, okay? So, from the second equation, dy dt, see, now I know it. Dy dt is minus x dot minus x. A little messy, right? dy dt is minus x dot minus x. So, get dy dt is equal to the negative of, let's do dx dt. I guess I get a negative 2c1 sine 2t plus 2c2 cosine of 2t. And then I guess minus t over 2. Right? That gives me dx dt minus t over 2. And then we need minus x. So we get minus c1 cosine 2t minus c sub 2 sine of 2t minus an 1/8 plus t squared over 4. Okay. I'm not going to do all the steps, basically. You know what you do. You bring all your sines and cosines together and you simplify, right? And notice, after you do the integrations, you get a constant integration from dy dt. So it'll be an arbitrary constant C3. So when you integrate this and add on the arbitrary constant, here's what you're going to get. You'll find out that y of t is equal to, this is all simplified, minus a half c1 plus 2c2 sine of 2t minus a half again, 2c1 minus c2 cosine of 2t plus t cubed over 12. Okay, the t cubed came because we integrated that one, right? Remember where that comes. Plus a quarter t squared minus an 1/8 of t plus c sub 3. Okay, don't forget that c3. Okay? So there's your solution for y now. Okay? And it's interesting, notice how the constants, because we chose to integrate x first, is simply just a C1, C2. And notice the kind of weird combinations of C1, C2 appear over here. That's demanded by the fact that dy dt is given in terms of x and x dot, okay? Had you solved for y first, then you'd probably have some stuff over here with just a C1, a C2, and then this guy would have all this mess with the C1s and C2s. But again, they're equivalent solutions, right? You apply initial conditions, you get exactly the same answer. Okay, any question on this or the procedure? Okay. So that would be the second example, I guess. And here's a third. Okay. And again, I don't know if we're going to finish, this stuff today, but just like the other lecture, the one over there, it's going to be an application, the one that I did on the video last week. You see some interesting applications of this to like things with pendulums and what else I have. I got some nice mechanical problems that you can solve using this technique of simultaneous equations. Okay, let's go to the third example then. Of course, there'll be homework on this, but obviously not going to be due for the exam. First equation, 2 times dx dt minus 3x plus y, 2x dot minus x plus y equals 4e to the t. Okay. So 2x dot minus 3x plus y. X dot minus 3x plus y equals 4e to the t, x plus 2 dy dt. X plus 2 dy dt minus 3y equals 0. So we read that again. So we got 2x dot minus 3x plus y equals 4e to the t. Next guy is x plus 2 dy dt minus 3y equals 0. Okay. First thing we're going to ask ourselves, what's the order? Okay, the highest order I see is first in x and first in y, right? So, second order. That means it should be 2 and only 2 arbitrary constants in the general solution. Okay. So again, we make things simple. We'll use that d notation. 2 d minus 3 operating on x, right? That's my 2x dot minus 3x plus y is equal to 4 exponential of t. And this guy looks like just a simple x over here. And then 2d minus 3. Same thing, but on the other variable, right? Is equal to 0. Okay, I think you see over here it doesn't make a difference. It's equally, same amount of work if you eliminate x or y, right? Let's see what I do. So I said, I eliminated x, I guess. Okay, so let's see what did I do? Eliminate x. So I guess I multiplied this one by 1 and this guy by 2d minus 3, right? Okay. So the first equation, okay, just becomes the same. It's 2d minus 3 operating on x plus 4, plus y, right? Is equal to 4e to the t. Hit this with 2d minus 3. 2d minus 3 operating on x. Then we get a 2d minus 3, that operator squared, right? Equals, fortunately, 0, right? Okay? So what I'm going to do now is just subtract these equations. Again, I'll subtract the second one from the first. So I get 2d minus 3, the whole thing squared, minus 1 operating on y. t minus 3, the whole thing squared on y minus y equals minus 4 e to the t. Okay? So, let's see what happens over here. I get 4d squared, right? Minus 60 is minus 12d. I get plus 9 minus 1 plus 8. Operate on y equals minus 4 e to the t. Right? 4d squared minus 12d. Okay. Then let's divide through by 4. D squared minus 3d plus 8. And this is right in the normal notation. We have the second derivative of y with respect to t. Okay. Divide through by 4. Minus 3 dy dt. Plus 2y equals minus, I'm sorry, I divided by 4, so it's negative exponential t. Right? Squared minus 3 plus 2 equals minus 1. Okay. So, second order equation on y, constant coefficients, not homogeneous. Again, variation of parameters maybe, we'll see. Not variation of parameters, I mean undetermined coefficients. Okay, so we've got a non-homogeneous equation on y. Let's solve the associated homogeneous equation first. Okay, what's the characteristic equation there? It's going to be r squared minus 3r plus 2 is equal to 0. That's really just r minus 2, r minus 1 equals 0. Right? So the roots of 1 and 2. So e to t and e to 2t in this case, right? So the complementary solution for y sub c is some arbitrary constant e to the t plus another arbitrary constant e to the 2t, right? Those are linearly independent solutions of the homogeneous equation. Okay. Now, what do we have to do? We have to solve the inhomogeneous equation, right? Okay. So let's look for a particular solution. What do we do? Well, I think the easiest thing to do over here is just look at the family, right? The right-hand side is minus e to the t, right? So the family of minus e to the t is this function e to the t, right? That's easy. Again, what's the thing you always have to do? After you do that, go back and ask yourself, is e to t one of the homogeneous solutions? And in this case, it is, okay? So therefore, we have to modify that to t e to the t. And again, you're doing this on the exam and you forgot to do that. Like I said, it's understandable, What would happen is that if you forgot to modify the family and you put for the particular solution some constant e to t, it would just drop out. You get 0. And then you have the dilemma, 0 equals e to the minus e to the t. So you say, how did that happen, okay? So that's kind of a key, okay? If you plug something in and it just drops out somehow, the coefficient drops out, you probably forgot to check that's a homogeneous solution. Okay, but we were careful, okay? So now, the particular solution is what? Some constant be determined, t e to the t. Right? And hopefully when we do L operating on yp, we're able to get the coefficient big A so that it goes to minus e to t. How many differentiations I've got? Nuts, I got to do 2 of them. Well, okay, things could be worse. Yp dot, yes, you get A e to the t, t plus 1, is that right? Let me just do it quickly. I get at e to t, at e to t plus a e to t, yeah. And yp double dot, I'll differentiate a e to t, I differentiate that, I get 1, right? That plus a e to t. I do a to t to differentiate that, plus 3 t plus 2. Right? A e to the t plus a e to the t. Okay. So now we have all our derivatives. Okay, we plug in the left-hand side and we equate it to the right-hand side there. L operating on y particular is what? You need y particular second derivative, which is a e to the t, parentheses, t plus 2, minus 3 times the first derivative of yp, which is a e to the t, t plus 1. Oh yeah, plus 2 times the particular solution. 2 times yp, which is 2at e to t. Okay, let's see what we can do over here. We have a e to the t. We got a t plus 2 over here, right? A e to the t minus 3t minus 3. Right? And then plus 2 a e to t plus 2t. Yeah, t's canceled. Everybody see how the t stuff goes out? You got t minus 3t, which is negative 2t plus 2t goes out, and you're just left with a 2 minus 3, I guess, which is a negative 1. So you get minus a e to the t. But we know that that has to equal minus e to the t. So therefore, the coefficient a that we're looking for is plus 1. Okay. So now we put everything together to get y of t. It's the complementary solution which we have someplace. There it is, right? C1 e to the t plus c sub 2 e to the 2t. And then the particular solution, we assumed cap a t e to t, the a was equal to a plus 1.